Chapter 4 is basically the continuation of Chapter 3. In Chapter 3, we introduce three kind of moments, and how are we going to calculate the resultant force and the resultant moment. And that's the basis for Chapter 4. So in Chapter 4, we basically talk about the equilibrium of rigid bodies. In other words, if we have a lot of forces or moments acting on certain rigid body, is overall the whole system is under equilibrium, then we can find out any supports or any unknown applied forces acting on the rigid body. And basically, we're going to talk about this kind of concept in two-dimensional and three-dimensional categories. For two-dimensional problem, the bottom line is, after we establish what we call the free body diagram, then we need to write down three equations. And these are the equilibrium equations we can get from Newton's law. For three-dimensional problem, later on we're going to talk about, is basically to establish a free body diagram and then write down six governing equations, six equilibrium equations. Okay? So today we're going to continue with Chapter 2. For two-dimensional free body diagram, so typically those three equations are here. Pretty much almost 90% of problem can be easily solved by using these three equations. In fact, almost 100% problem can be solved by this one. Although sometime, occasionally, these three equations may not be the best equations. But if you do not know how to establish other equations, I just suggest you to do this. And today I'm going to give you an example to let you know this three equations with a combination is very powerful to solve any difficult problem. And you just need to combine these three equations to solve those unknowns in a very straightforward way. Okay? Last time I talked about this example. First of all, you need to draw the free body diagram using all the forces to represent the interaction from the rigid body to the outside world. And there's another example I talk about as well. So this time you need to pay a little bit attention about the cable. Sometimes if there's a cable connecting 2 points, both of which are with the rigid body, then basically you don't have to cut. If you cut, then you have to give these two forces always canceling each other. That's really no need to cut. However, for those questions I assigned, which you're supposed to do this week, sometime when you look at the cable, both ends are part of the rigid body, but somewhere in between it is connected to another support. And if that's the case, you still need to cut. Because if you do not cut the cable, somewhere in between connecting to an outside connection, then you are having this outside support as part of rigid body. That is not allowed. So that's why you need to be more careful. I'm saying if you have 2 points connecting a certain cable, both of which are in the rigid body, you don't need to cut. But that's under another condition. Somewhere in between, nowhere is connected to outside. If it's still connected to outside, then you have to cut as well. Okay, so today I'm going to talk about another two scenarios which can make the problem much easier to solve. First of all, I want to talk about special case, which is called the two-force body. The reason we need to introduce this one, because next in Chapter 6, when we talk about trusses are all what we call the two-force body members. So that's why it's important, although it's straightforward. If you have a rigid body, for example, something like this, where you can draw the general rigid body is not a problem. If there are only two forces acting on different locations, for example, you have one force acting on point A, you have another force acting on point B, then what? The conclusion is these two forces must have the same magnitude, but in the opposite direction. And also, the direction is between point A and point B with those two forces applying on. So that's the conclusion. The only requirement is if there are only two forces acting on the rigid body. It can be anywhere. So then the conclusion is these two forces has to be in the same direction but in the opposite sense, and the magnitudes are the same. It's very easy to demonstrate that, because if you are looking at this scenario, you need to establish the free body diagram. And what you can do is, for example, you connect between A and B like this. Okay, and let's say this is one of the, this is any force direction. You connect to this one. Then let's say we take the moment equation at point A. So then this force So this force will now be involved in that moment equation because this force, Fd, d equal to 0. So then the moment due to this force equal to F times d. So what is the F? F is the magnitude of F2. But what is the d? D is a shorter distance. So for example, if this is in this direction, this is a shorter distance. But F times b must be equal to 0 to satisfy the equilibrium condition. So then the only thing you can make that equation F2 times d equal to 0 is to have a d equal to 0. If d equals 0, that means the force line must be along this direction so that the shorter distance from the second force F2 is also 0. So that is what we call the direction of this force 2 must be along the AB direction. Similarly, if you want to take a moment at point B, then this force will now be involved. And then what is the moment of F1 at point B? So then it's still F1 times d. So d is a shorter distance from B to this force line. But the result of the product, F1 times d must be equal to 0. And then the only way you can make it 0 is have this d equal to 0. So then this force must be along this direction as well. So then when you are collecting all forces in this direction equal to 0, then F1 minus F2 must be equal to 0. So the final conclusion is, if you have a rigid body with only two forces applied on different locations, then these two forces must have the same magnitude, the direction in AB direction, but they are in the opposite direction. It could be in compression. This is look like a tension, right? It can be in compressive direction. This is a very useful conclusion normally we use, including some of the questions you're going to see based on the assignment. Another special situation is what we call the three-force body. So this time, when we have a rigid body, there are three forces acting on three locations in this rigid body. Then what? The conclusion is all these three forces must be concurrent. So the conclusion is the line of action of the three forces must be concurrent. What that means is you have general two forces. These two forces, as long as they are not parallel, you can find a common point. Or let's say these two forces, for example, this and this one, you have a common point so that the forces are passing point D. Then the third force must going through this point D as well. So that this is called the line of action of three forces must be concurrent. And the reason we have this conclusion is also very easy to demonstrate because, first of all, when you are collecting this point D based on these two force lines, then you take a moment of all forces at this point D. And that's going to end up the same thing because F1 is passing through this point, then there's no moment. F2 is also passing through this point, then there's no moment contribution. So you only have F3 times D, and but equals 0. But F3 itself is never to be equal to 0. Then the only thing you can make F3 times D equals 0 is to have a D equal to 0. If D equals 0, that means then the force line must go through this point D as well, so that the shorter distance equals 0. Okay? So that's the conclusion. But in fact, we rarely use such conclusion. The reason is, if you want to use a geometrical method to solve certain problems, then this conclusion is very useful. But typically, we use a component method to solve all the equilibrium problems in terms of calculating the x and y component of forces. Then this conclusion is not very useful, in fact. But I do want to mention this one just to let you know that if you do want to use a geometrical way to solve problem, and then this is the conclusion you could use. So let me give you a simple example. We have a 10 kilogram joist like this. The total length is 4 meters. From A to B is a 4 meters. And there is a rope connecting to point B and this gentleman, so that this gentleman can put out the rope to maintain this overall rigid body in equilibrium. So then the question is, and also the angle is given 45 degrees, and this angle is 25 degrees. So the question is, how can we calculate the magnitude, or called the tension in the rope or the cable, and the reaction of point A? So obviously, there's a typical two-dimensional problem, depending on how are we going to solve it. So in fact, I would like to use component method to solve this problem. You can see later on it's very straightforward. But just in case you want to take advantage of what we call the three-force body with a conclusion called all three forces are concurrent in terms of their directions, then you can also solve this problem. But it's not that easy, in fact, even though you can plot the free body diagram in a very straightforward way. First of all, whenever we see this kind of problem, number one, the first step, we need to plot the free body diagram. Okay? So we need to identify the rigid body, which is this one from A to B. So once we plot the rigid body, then we just want to see how this rigid body is interacting from outside world. First of all, they gave you the self-weight. So if they gave you the self-weight, then you need to put the self-weight force at the center of this rigid body. So from A to B, the center is at the middle point. So first of all, you find out the middle point, you call G, and then you gave this force, which is called the self-weight, W. So W is due to the 10 kilogram self-weight. The kilogram is now the unit of force. So that's why you need to have a 10 multiplied with 9.81. So you end up with 98.1 Newton. And by the way, this is an international unit. So every time when you see the kilogram, you do need to transfer from kilogram to Newton. But for US unit of system, you don't need to multiply with 9.81, because normally when we talk about the self-weight in terms of the US unit, we just tell you that's how many pounds. And pounds itself is the force unit. So that's why you don't need to multiply 9.81 for any pounds kind of unit. Second, there is a rope connecting between this point and this point B. So then obviously you can cut this cable or this rope so that you're going to give a force. You're going to give a force in this direction. And this direction is with a 25 degree here because it's given here. And finally, you have a support point A. If you look at the support point A, so obviously this point A is at a corner here. So this point cannot move vertically. It cannot move horizontally either because there's a kind of a small wall here, right? So then when you are using the certain support reactions to represent the support point A, then you are basically having two forces, X direction, Y direction, or you can put these two forces together to give a total force called R, but you don't know the direction. So either way, you can have two horizontal vertical components where you give one direction, but now the angle is unknown. Okay? So if you plot something like this, then you will see this rigid body is with three forces. So if you go back to look at this one, if there are three forces acting on the rigid body, it's called a three-force body. Then the conclusion is the line of action of three forces must be concurrent. Or in the extreme special case, they are parallel, but nobody can see real parallel forces. So if they are concurrent, what that means is you can have this force and this force forming a common point you call point C. Because this force is vertical due to the self-weight, and this force, the direction is given because 25 degree, so you can easily find out point C. Then, based on that conclusion from three-force body, this reaction must go through this point as well, so that these three forces are concurrent in terms of their force directions. So, if this force is going through this point C, then basically you can determine this angle without using the equilibrium equation. In other words, you can totally determine this angle based on the geometry we have. So for example, we have this rigid body here. This is a 45 degree given from the original problem here. This is a 25 degree. This is a 25 degree. This is also 45 degree if you build this triangle. And then this is alpha we want to calculate. Okay? So with this angle, and then the length from here to here is 10. And then we also have from here to here is 4. So basically, you can calculate this angle. You can calculate this angle because you know the length of this one, and you also know this length because the total is given. But this one from here to here, you can fill this form, fill this point. Then you get this length so that you get this one. You get this angle, and then you can get this angle. The details are here. Finally, you end up with alpha equal to 58 degree. But basically, I don't like this method because it has too many geometries issues involved. Then basically, there's really no need to use this way. what I'm trying to show you is use another way to solve this problem, which is use a component method, which I emphasized since chapter 2, to solve the same problem, and then we can compare result. So I'm going to use the dot camera. to solve the same problem. Okay, so we still follow the same step. Number one, we need to plot the free body diagrams. So how to plot the free body diagram? First of all, we need to identify the rigid body. So this is point A, and this is point B. And the angle between A and B is 45 degrees. So first of all, there's a force due to the self-weight. It's called G. And that is 10 times 9.81 in terms of Newton. Second, at point B, there is a force with an angle 25 degrees here. Finally, at point A, there's a reaction. And the reaction should give you two forces. And this one, let's call RAX. And this one, I call RAY. These are two unknown forces. So this is what we call the free body diagram. Instead of using what we call the concurrent forces concept, we basically just want to use the three equations, equilibrium equations. To solve this problem. In other words, we just need to collect all forces in x direction and set equal 0. We need to collect all forces in y direction and set equal 0. And then we need to collect a moment equation at a certain point. So let's do one by one. So let's say this is the x direction and this is the y direction. And let's collect all the forces in different directions. In x direction, number one, you have RAX going to the right. And number two, you have this force, the cable. Then the x components of that cable is this. So this total is 45 degrees, and this is 25. Then this angle should be 20. So then this force, I need to give a name. It's called let's call FB. So FB times sine 20. I'm sorry, cosine 20. So this is 20, then cosine is this. So FB times cosine 20 should be the x components of FB. But this is to the left, so that's why I need to give a negative sign. And then there's no other forces, and that's equal 0. So that's the first equation, collecting all the x component of forces, and set equal 0. The second equation is for y components. So for y component, number one, you have RAY, and you have a G going down, that's minus G. And then this force FB should also have a y components, so that's going to be FB times sine 20 degrees. And this one is going down, so then it's negative as well, and that's equal 0. So that's the second equation. Any questions? Third equation, which is a moment equation. So we need to take the moment at a certain point. On which point you want to take? You can take any point you like, point A, point B, and somewhere in the center, point C or point H. But we'd better take this point, right? So if I take point A, then these two unknowns, RAX and RAY, will not be involved in that third equation. So that's a typical way we want to pick the point. So then, if we take point A, so then RAX is gone, RAY, there's no contribution. So first of all, let's look at G. So we use F times D, for example, right? So G is a magnitude times the shorter distance. So here is the shorter distance, this one. So what is shorter distance? So from here to H, total is 4, from here 4 meters. So from here to here 2 meters, right? So 2 meters times sine 45 degrees. That's the shorter distance, this one. 2 times sine 45 degree. Same thing, in fact. Yes, cosine, that should be more appropriate. But sine and cosine are the same, 45 degree. Okay, so let's put cosine. Okay, so this is the moment of this G at point A. So that's the first one. And then how about this force, FB? So then you may say, well, FB times the shorter distance. So the shorter distance is probably here, right? So this is a shorter distance. So then FB times shorter distance. So this triangle, you have 25 degree, and this is 4. So 4 times, this time is cosine 25 degree. Oh, sine, I'm sorry. Let me rewrite, okay. So FB 4 times sine 25 degree. And I forgot to give you the directions. So in terms of force G, it's going down. If you hold point A, so this point G should have the potential to rotate rigid body clockwise. So it's negative sign in the front. And then this force should have the counterclockwise rotation. So that's positive. And that's go 0. Okay? So these are the 3 equations. Equation 1, equation 2, and the equation 3. So when you combine those 3 equations, then you can easily calculate these 3 forces, which is called RAX, RAY, and then FB. Okay, so let me give the answer for these 3 magnitudes. Okay, so FB is 81.9 Newton. Okay, and then actually RAX, RAY, the book doesn't give me this. The combining this one, the magnitude of this R, which is RAX plus RAY square, and square root is 147.8 Newton. And then the direction is the alpha is 58.6 degree. So because I don't have this result directly, but I can write it down. 147.8 with this angle you call the 58. That's gonna be cosine 58.6 degree, and that's in terms of Newton. And then RY, that should be 147.8 times sine 58.6 Newton. Okay? And you can punch your calculator to get it because I didn't write down the 2 components. So if you look at the way we're trying to solve this problem, it's very straightforward if you use component method. Of course, if you do not want to use component method, you want to come back to see how the geometrical way to solve the same problem. First of all, you have to understand what we call the concurrent forces by building these 3 forces passing through the same point C. And then first of all, you can determine this angle, which is 58.6. And then from this triangle, you can use law of sines to calculate the 3 components. But in general, I don't like this method because I believe the component method is very straightforward. It doesn't really matter how many forces you apply on the rigid body. You can always solve the problem. And this method has certain limitations because you have to have only 3 forces acting on the rigid body. So really up to you. If you want to follow this one, it's not a problem. If you do it correctly, you can get the same answer. But if you want to use the way I was showing you here, I believe that is more straightforward. This one. So you basically just need to collect the 3 equations based on fx equals 0, fy equals 0, and then the moment equation equals 0. and you can solve the problem. Of course, you may say, wow, from these three equations, I have to combine all these three in order to solve these three unknowns. And the answer is yes. But that's mathematics, right? So you just need to know how to solve these algebra equations from those given equations to solve the same number of unknowns. Any questions?
Yeah, could you just explain how you got the equation for the moment?
Okay. The third equation, which is here. Let me see if you can see it. Okay. So first of all, we need to find a point based on this free body diagram. So you can find other point, that's not a problem. But if we pick point A, then these two reactions, Rax, Ray, will not be involved. In other words, the moment of Rx at point A equals 0, because the short distance d equals 0, passing through this. The moment of Ray at point A equals 0, because, again, the d equals 0 is passing through this point. So that's why we don't need to worry about these two. Now, let's worry about force G and that force FB. This area is quite crowded, so let me just replot this one, and I'm pretty sure you can understand it. Okay, so if I replot this, make it bigger. This is point A. I have a force G. I think you are probably trying to see how this force FB, the moment of FB at point A, right? So let's collect all the moment at point A set equals 0. Number one, FB. FB need to times D. And if you hold this point A, so FB should be counterclockwise, so it's positive. This is G. G is clockwise, so negative G times another D for this one, and that's equals 0. So we just need to figure out these two D's, which is called short distance. We do one by one. First of all, what is the short distance from this point to this force line? So then this is short distance. Okay? So this is short distance. So then this D should be from this triangle. This is a right angle here, and this is 25 degrees. So from here to point B is a 4 meter. So 4 meter times sine 25. That should be the short distance. Oh. Okay? And then, what is the short distance from point A to this line? This is a short distance, and that's easier. This is a 45 degree, and from here to here is 2 meter. So that this one should be 2 times cosine 45 degree. Okay? Any other questions? Yes?
If you try doing the R cross FB to get the moment, would it work?
Yes, it should also work. So then what you need to do is to look at this contribution again. You just use R cross F. Okay? So then this R should be the distance vector from point A to point B. You need to build that R and J. And then I plus something with J, and then cross this F. But this F should be the X components I plus FB Y component and J. You should end up with the same result if you do it correctly. Any other questions? Okay, so back to this one. So finally you end up with equation 1, equation 2, and equation 3. You combine all these three equations together. You solve for Rax, Ray, and Fe. And that's the answer the question asks you to solve for, right? Any other questions?
How are you able to determine which reaction point it was?
Okay, for this problem, there are two ways you can find out the reaction from point A. Because normally at point A, if there's only like a flat surface, so obviously there is a reaction in the vertical direction. You may not be sure whether there is a horizontal resistance or not, depending on the problem statement. If the statement said if it's frictionless, then you don't have this. But that is different from this real scenario because this is exactly on the corner. In other words, at this point A, you cannot move down, but you cannot move to the left either. So that's why there are two reactions in both x and y directions.